All right, class, today we're going to start our new unit on sequences and series, and we did a little bit of it in class today. A sequence is a function whose domain is a set of consecutive integers, and the terms are the values in the range of the sequence. And what we didn't work on is the concept of series, and the series is the expression that results when the terms of a sequence are added together. And in order to know that we're talking about a series and not a sequence is the summation notation. And the summation notation determines that you're dealing with sums, and that notation is indicated by this big uppercase sigma. Okay? So we've been working with sequences, and the domains are integers. Some of the domains start with 1 and go all the way up to n. Other domains sometimes start with 0 and go all the way up to n. So it really does depend on who's writing the sequence. But your starting term number is either 1 or 0. And the term of the sequence is indicated by the labeling of the sequence, which is a letter, alphabet letter, and the sub component, which is the term number. So the first number in the sequence is a sub 1, or if the first number is 0, a sub 0. There are two types of sequences. There are finite sequences, and those are sequences that have a certain number of terms. In other words, it only has 6 terms or 12 terms or 100 terms. That's a finite sequence. It goes A1 all the way up to A100 or whatever. And then there's an infinite sequence, which the sequence continues without stopping. And so you know the difference because of the way they list it. 2, 4, 6, 8 means finite, and 2, 4, 6, 8 with dots means it keeps on going. So there are two ways that you can define a sequence. By the rule can be both recursive or closed form. In this case, this is an example of recursive, which means it depends on the previous amount. And closed form, this is an example of closed form. These are both closed form. So to write a series, remember we talked about series or summing a sequence. So you can use the summation notation to write a series. And this is very new. You haven't seen it before. And every summation series has 3 components. It has, of course, the lovely summation symbol. It has the starting value, I is equal to 1. So we start with, in this case, the first term is a 1 term, not a 0 term, and then the last term is up at the top. So this is a finite sequence because it goes from terms 1 all the way up to 4 terms. So you're only talking about, this is term 1, term 2, term 3, term 4. But if it's an infinite series, then now it looks the exact same, except up here at the top, since it goes on forever, you're going to have an infinity. Or sometimes they don't even put anything up there to indicate that it's going to keep on going forever. So the terminology is new. The index of summation is I, which means it could be any lowercase letter as long as it's not uppercase letter, and we usually use I. And the lower limit in this case is 1, but sometimes it can be 0. The upper limit of summation is 4 for the finite series, and for the infinite series, it's infinity. Summation notation is also called sigma notation because this actual letter is the Greek alphabet letter sigma. Okay? So here we have some popular summation series, and I will list them. I'll do a couple of examples. So in this case, let's say if I were to match it out, if n is equal to 3, then I'm just going to take 1 and do 1 3 times. And so the summation of that is going to be exactly whatever n is. 1 plus 1 plus 1 is 3. But what if n is 7? And that means I'm taking n 1 out 7 times and adding 1, the number 1, to itself 7 times, and of course the sum is of course 7. So in order to figure out the value of this series for n, it's just n. But that's the simple case. Now let's take a look at a more difficult case, which is instead of summing the number 1, we're going to be summing the value I as I changes from 1 to n. So when n is 3, then you start off with 1, then you increase the value to 2, Then you increase the value to the next value, which is 3. And the sum of that is going to be, sorry, did I say 6? Okay, but another way you can figure that out is by taking the number n, which in our case is 3, multiplying it times n plus 1, which is 4, and dividing by 2. So 3 times 4 is 12, divided by 2 is 6. We still get the same answer. Let's see if it happens if we change n to 7. When n is 7, that means we take the summation is I from 1 to 7, so 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, which is 28. But we can also figure that out by taking 7, multiplying it times 7 plus 1, which is 8, and then dividing by 2, and we still get 28. So let's start with examples on page 172. What are the first 6 terms of this sequence? It's a sequence on a series because we're not summing up the term values. So a sub 1 is 2 to the 1 plus 1, which is 4. A sub 2 is 2 to the 2 plus 1, which is 2 to the 3rd, which is 8. And a sub 3 is 2 to the 3 plus 1, which is 2 to the 4, which is 16, and vice versa. And that's how you can figure out these terms. Now we can also figure out these terms by doing the recursive formula, which is figuring out the term based off the next value. This is closed form, but we can look at an example of recursive. If you start with 4, what do I multiply by 4 to get 8? 2. What do I multiply by 8 to get 16? 2. 16 times 2 is 32. 16 times 2 is 64. So another way I can name this sequence recursively is a sub n is equal to 2 times a sub n minus 1. Okay, so both of these terms represent the exact same sequence. Okay, over here, describe the pattern, write the next term, and write a rule for the nth term. So in this case, we see 1, 4, 9, 16. Well, some of you may recognize that those are perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and vice versa. So that means the next term is going to be 5 squared, which is equal to 25. So a rule for the term in closed form is n squared. Okay, in recursive form, that's going to be a little bit difficult, but it can be done by doing something else, but we're not going to focus on that. So over here, let's take a look at the second term is 0, 7, 26, 63. And that looks a little bit more difficult to figure out. But let's see what happens if I write the term as something subtract 1. So let's say 1 to the 3rd subtract 1 is 0. 2 to the 3rd subtract 1 is 7 because 2 to the 3rd is 8. 3 to the 3rd subtract 1 is 26 because 3 to the 3rd is 27. So 27 minus 1, and 4 to the 3rd, and vice versa. So that means the 5th term is 5 to the 3rd minus 1. 5 to the 3rd is 125, so minus 1 is 124. So the rule is the closed form rule is n to the 3rd minus 1. Now let's take a look at some examples. Write the series using summation notation. So as you can see, this is not a sequence because it does have addition involved. So this is a series. And we have to figure out what our starting term is and what our ending term is. And it's a finite series because, as you see, it starts with something and it ends with something. So the first term is 4. But to go from the 4 to 7, we add 3, so that's kind of like a linear expression. So that means the second term is going to be 3 times something plus 1 to give you 7. So that means it's 3 times 2 plus 1 to give you 7. The third term is 3 times 3 plus 1 to give us 10, and vice versa. So now we have here, and the last term is 3 times 15 plus 1. So that means what's changing each time is the number that I'm multiplying 3 by. So that means my a sub I has to look like 3 times I plus 1, where I starts off with 1 and then 2 and 3 and all the way up to, if you said 15, you were correct. So the lower limit is 1 and the upper limit is 15. So how do I express that? We do our summation symbol. I is equal to 1 all the way up to 15. And then what are we summing? We're summing 3 times I plus 1. Okay? So for each term, the denominator is So that's that example. Over here, we see for part B, we have a denominator is a perfect cube, 2 to the third, 3 to the third, 4 to the third. So a sub I looks like 1 over I to the third. So that means the lower limit is 1, but the upper limit, since it goes on forever, is infinity. And so that means that when we write our summation, it's going to look like this. I equals 1 all the way up to infinity because of the dot, dot, dot. And what are we adding up each time? We're adding up 1 over I to the third power. Okay? So on your own, if you could figure out the checkpoints to practice to see if you know how to write the series using the summation notation. Okay? All right, and that's it. I didn't want to be over 10 minutes, so it's 10 minutes and 46 seconds.